everybody, in this video we are going to go over section 7 of chapter 9, and here we are going to talk about matrices. We'll go over some basic definitions about about matrices and their dimensions. We will talk about matrix operations, namely addition, subtraction, scalar multiplication, and matrix multiplication, and then we will go over one application. Okay, why do we care about matrices? Well, it turns out that the simplest way, or the most straightforward way, or compact way to deal with the solution of linear systems is through its matrix representation. And with that in mind, we need to talk a little bit about matrices and how they're structured and how they can be used. So, this right here is an n by m matrix. It has m rows and n columns. Notice the first term tells you how many rows, the second dimension tells you how many columns. Each element in its general sense has two subscripts. The first subscript tells you which row it is, or at least should be in. That one is wrong. This should be A21. And the second subscript tells you which column it is in. So this is in the first column, the nth row. This is in the first column, the third row, and this should be A21. There we go. The first column, the second row. Okay, a square matrix of order n is, as you guessed, is basically an n by n matrix, n rows, n columns. We also have a row matrix, and this is a row matrix. It has one row and n columns. Here they are. And then we also have a column matrix, which has one column, but can have as many as n rows, where of course n is an integer. Now, we say that two matrices are equal if these two conditions are satisfied. They have the exact same dimensions, and all of the corresponding elements are equal. So with that in mind, these two matrices are equal. They're both 2 by 2 matrices, and every single element is the same. These two matrices are not equal, even though they have the exact same dimension. The last element, here we have a 4 and a -4. As a consequence, they are not the same. Now, one of the very first things you're going to have to do in your homework is determine the dimensions of a matrix. Okay, and so let's do that here. Here we have two matrices. Part A, we have, well, this one has 1, 2, 3 rows and 1, 2, 3 columns. This is a 3 by 3 matrix. Not only that, well, that's weird. This is a square matrix. This one has 1, 2 rows, 3 columns, so this is a 2 by 3 matrix. This is not any special matrix, i.e. it's not a square matrix or a row matrix or a vector or a column matrix, so it's just a regular matrix. Another set of problems that you will find in your homework is something like this. Here we want to find the values that make the two matrices equal. So for part A, remember we want for two matrices to be equal, they have to have the exact same dimension, and then they also have to have the exact same elements. So here, since this one is a -3, we would want A to be -3. I don't know why it's doing that. Since this is 9, we will want B to be equal to 9. Since this is -5, this actually should be a C. We want C to be equal to -5. And then since this is 0, we would want D to be equal to 0. Okay, now, for this one, notice this is a 1 by 2 matrix, and this is a 2 by 1 matrix. These could never be equal, so there is no solution. There's no way to make these matrices equal. So we would say that there's no solution. Okay, what about the addition and subtraction of matrices? Well, they can only occur if the matrices have the exact same dimension. If they do not have the exact same dimension, they cannot be added and they cannot be subtracted. If they do have the exact same dimensions, then the addition of two matrices is basically it's tantamount to the addition of each corresponding element. And subtraction and to subtract two matrices, you would subtract each of the corresponding elements. And we can show that in this example here. So for part A, we can add this 2 by 2 matrix to this 2 by 2 matrix. And if we do, well, we're going to get a 2 by 2 matrix. The first element is going to be 3 plus 7, which is 10. A12 is going to be negative 8 plus negative 5, which is negative 13. A21 is going to be negative 4 plus 10, which is 6. And then A22 is going to be 6 plus negative 6, which is 0. Now for part B, this addition is not possible because they do not have the same dimension. Okay, notice that this right here is a 2 by 3 matrix, and this is a 3 by 2 matrix, so therefore they cannot be added. Okay, for this example, we want to subtract our matrices, and once again, we just do the subtraction element by element. Here we have 8 minus negative 8, that will be 16. Negative 9 minus 4 is going to be negative 13. Negative 6 minus negative 7, that's going to be negative 6 plus 7, or 1. And then 2 minus 11 is going to be negative 9. Okay, and now these have the same dimensions as well. So we can go ahead and do these term by term. 9, or element by element. 9 minus 18 is negative 9. Negative 3 minus 12 is negative 15. Negative 6 minus a negative 6, well, that's basically 6 plus 6, or 12. Now let's talk about some special matrices. The first one is the zero matrix, and as you might guess, a zero matrix is a matrix that contains zeros. So here you go. Here's a couple of examples of them. And now we also want to talk about the additive inverse. Okay, now the additive inverse of a matrix A is that matrix, and we're going to call it negative A, which which is defined in such a way that if you add the two matrices together, you get 0. And you can see that basically negative A is going to be the negative of all the values here. And actually, this is how we define subtraction from an algebraic concept. It turns out that in the strict algebraic concept, subtraction, A minus A is actually addition, where we add A to its inverse to get our result, which is 0. So when actually you are doing the operation A minus B, what you're actually doing is you're adding A to the additive inverse of B. Does that really important now? No, but if you actually take a course in abstract algebra, you'll see it there. Okay, the next operation is scalar multiplication. Okay, so here we're going to let K be any real number, we're going to call this, and that's going to be our scalar. And then we're going to let A be any matrix of any dimension, it doesn't matter. So this was going to be A. If that's the case, then Ka is nothing more than a matrix where every single element is multiplied by the scalar K. That's all there is to it. And so with that in mind, let's take a look at this example. Okay, if we multiply this matrix by the scalar negative 3, what are we going to get? Well, we're going to get a new 2 by 2 matrix where this element is going to be negative 3 times 2, or negative 6. A12 is going to be negative 3 times negative 5, or positive 15. This is going to be positive 12, and this will be 0. So that's all there is to it. It's just basically element by element multiplication. Scalar multiplication does have some properties which can be useful. The first one is that the first property, two properties, is that they are distributive, and you can sort of see that here. The sum of C plus D times A is equal to CA plus DA. Similarly, this works. It works from this point. It works in the other direction, or it works for the matrices as well. And also, the scalar multiplication is associative, and this basically tells you that the order of the scalars relative to the matrix does not really make that much of a change. Okay, next we want to talk about matrix multiplication. And this is more of an example of how it works. I kind of gave you the blow by blow in your notes, but this is what I want you to see. Now notice here that I have a matrix, a 2 by 3 matrix, and I'm multiplying it by a 3 by 2 matrix. Now for multiplication to work, the inner dimensions, i.e. the number of rows here, the number of columns here, and the number of rows for this matrix must be the same. Like I could call this, let's suppose that I decided to when I write the matrix A, I write it by its dimension. I also put the dimensions in the subscripts. So I'm going to say that this kind of tells me that A is a 2 by 3 matrix, and I could call this B and write this as follows. B is a 3 by 2 matrix. If that's the case, then for matrix multiplication is only possible when the inner dimensions, the 3's right here, when these inner dimensions are the same. If they are the same, you can do multiplication. And then what are the dimensions of the result? What are the dimensions of the resultant matrix? Well, it's going to have that many rows, that many columns. It'll be a 2 by 2 matrix, as you can see here. Okay, so how does all this work? Well, the way that we're going to work is, the way this works is that to produce the first element, we are going to multiply the first row by the first column. That's going to give us A1, 1. A times 1 times 0, plus 3 times 4, plus 5 times 8. Okay? To get the second column in the first row, we're going to multiply the first row, the first row of the first matrix by the second column of the second matrix. That's going to be 1 times 2, 3 times 6, 5 times 10. And then similarly, for the first row for the first column of the second row, we're going to multiply each element of the second row by each element of the first column and add them up. So it's going to be 9 times 0, 11 times 4, 13 times 8, and then similarly for the last one, we're going to multiply the elements in the second row by the elements in the second column of the other matrix. That's going to give us 9 times 2, 11 times 6, and 13 times 10. And then when we add all these up, we will get 52, 70, 148, 212. And that is pretty much how we multiply matrices. Okay, and let's actually illustrate these in these two examples. So in this example, we want to multiply two matrices. So let's have it. Here we have A is equal to 3, 1, or is a 2 by 3 matrix, and B is a square matrix, which actually makes life a little easier for us. So here we want to multiply 3, 1, negative 4, 0, 5, and 6, which is a 2 by 3 matrix, by 4, 1, negative 3, 8. So A is a 2 by 3 matrix. We actually have 3 columns, and in B we only have 2 rows. Okay, for us to be able to multiply these two matrices, we have to have this. The number of columns in the first matrix must be equal to the number of rows in the second matrix. But here we don't have that, and 5 has nothing to multiply with, so this is not possible. Because we have 3 rows here and only 2 columns. Okay, now what about in the other direction? BA. Well, B is 4, 1, negative 3, 8, and then we're going to multiply that by A, which is 3, negative 4, 5, 1, 0, 6. Okay, now how are we going to do it? And then now this we can multiply. Here we have 2 columns and 2 rows, so this can be done. And what is this going to produce for us? It will produce for us a 2 by 3 matrix. Okay, so the first element is going to be equal to 4 times 3, which is 12, plus 1 times 1, which is 1. Okay. The second element is going to be 4 times negative 4, which is negative 16, plus 1 times 0, which is 0. And the third element is going to be 4 times 5, which is 20, plus 1 times 6, which is, well, 6. And then for the next column, we are going to have negative 3 times 3, which is 9, negative 9, plus 8 times 1, which is 8. That's going to be negative 9, plus 8. And then for a 2, we're going to have negative 3 times negative 4, which is 12, plus 8 times 0. And then finally, for the last one, we're going to have negative 3 times 5, which is negative 15, plus 8 times 6, which is 48. So the resulting product is going to be, well, 12 plus 1, that's 13. Negative 16 plus 0, negative 16. 20 plus 6, 26. Negative 9 plus 8, 1. 12 plus 0, 12. 48 minus 15 is going to be 35. And that is our matrix. Okay, what about when we're dealing with square matrices? Well, when we're dealing with square matrices, since all the dimensions are the same, we can actually find a product for AB and a product for BA. So let's take a look at AB. Here we're going to have 2, negative 6, negative 5, and 1. We're going to multiply that by 3, 2, negative 4, 3. Okay, so now for the first column, for the first element, A11, we're going to multiply the first row of the first matrix by the first column of the second matrix. So that's going to be 2 times 3, which is 6, plus negative 5 plus 2, which is negative 10. That's going to give us negative 4. Okay, now for this one, we're going to multiply the first column, the first row of this matrix by the second column of this matrix. That's going to be 2 times negative 4, which is 8, plus negative 5 times 3, which is negative 15. So negative 8 minus 15 is negative 23. And then we're going to have, then for this one, it's going to be the second row times the first column. That's going to be negative 6 times 3, which is negative 18, plus 1 times 2, that's going to be negative 18 plus 2, or negative 16. And then finally, for the last one, we're going to multiply this row by this column and add them up. Negative 6 times 4 is negative 6 times negative 4 is negative 24, plus 3 is negative 27. All right, now for BA, we are going to do 3, negative 4, 2, 3 times 2, negative 5, negative 5, negative 6, 1. Okay, and that's going to give us, for the first one, 6 plus 24, that will be 30. Okay, for A12, that is going to be negative 15 minus 4, that's going to be negative 19. Okay, now for A21, I'm sorry, that's going to be this row times this column. 2 times 2 is 4. 3 times negative 6 is negative 18. 4 minus 18 is negative 14. And then finally, multiplying this row by this column, we're going to have 2 times negative 5, which is negative 10, plus 3, that's negative 7. Now notice that these two matrices are not the same. What does that tell us? That tells us that matrix multiplication is not commutative. However, matrix multiplication is associative. You can actually change the grouping, and that won't That won't change anything. You just can't change the order, but you can change the grouping, and they are distributive. So these two properties do hold. And this leads us to our last problem, which is an application. And I need more room to do this. So what I'm going to do is I'm going to move this over to OneNote, and we will deal with it there. Okay, so here we are. So this application is actually the second to last problem in your homework, and this is what we got. Okay, so here we have Yummy Yogurt. It sells 3 types of yogurt: non-fat, regular, and super creamy at 3 locations, and those locations are 1, 2, and 3. And we have some information about what they sell and whatnot. The first thing we need to do is write a 3x3 matrix that shows the sales figures of the 3 locations with the rows representing the locations. So we actually want to create a matrix where the rows are location 1, location 2, and location 3. And then we want the columns to be non-fat, regular, and super creamy. So the matrix is, so we're going to have a 3x3 matrix, and each element is going to correspond to, or each row is going to correspond to the location. So let's take a look at how this is going to go. Location 1 sells 20 gallons of non-fat yogurt. So that's going to be 20 here. 110 gallons of regular yogurt. Well, that's 110 right here. And then 40 gallons of super creamy yogurt. That's going to be 40 right here. Okay. Location 2 sells 30 gallons of non-fat yogurt, so that's 30 for location 2. And location 3 sells also 30 gallons of non-fat yogurt, so that's a big 30 here. Okay. Daily sales of regular yogurt are 70 for location 2 and 150 at location 3, so that is 70, 150. And then we have that at location 2, 40 gallons of super creamy are sold, and the same thing at location 3. So this is 40, 40. Okay, so that is part A. So A is done. Boom. Okay, part B tells us that the incomes per gallon for non-fat, regular, and super creamy are $12, $11, and $15. And we want to write a 1x3 matrix or a 3x1 matrix displaying the incomes. We want to select and we want to select the correct choice below with this. That's part of the ML part, and fill in the box to complete that particular choice. And what you want to do is you want to do this in such a way that we can actually multiply the two matrices, because that's what's coming up with C. Okay. So we actually want to write a 3x1 matrix. We don't want to do a 1x3 matrix displaying the incomes. And that will give us, and in that case, our matrix is going to look like this. It's going to have 12 here, and then it is going to have 11 here, and then 15. And then step 3 is to find the product of it, and then step, so this is B, and then step 3 is to find the matrix problem that gives the daily income at each of the 3 locations. So the daily income for location 1 is, so if we actually multiply this matrix by this matrix, we will get the daily location, or we will get the daily income for location 1. The second element will be the daily income for location 2, and the third element will be the daily income for location 3. Okay, so the first element of the result of our resulting matrix is going to be 20 times 12 plus 110 times 40. No, I'm sorry, 110 times 11 plus 40 times 15. Okay, now to get the location 2, it's going to be this row times this column. So that will be 30 times 12 plus 70 times 11 plus 40 times 15. And then finally for location 3, it is going to be 30 times 12 plus 150 times 11 plus, well, once again, 40 times 15. And that will give us 2050, 1730, and 2610. And then the last part, there is actually a part D, and that is to compute the total income. So this was C. So D is to compute the total income. That's going to be the sum of all these. And that will be $6,390. And that is all that I have for this video. If you have any questions, please feel free to contact me. This is Bob Boyle, signing off.